Hello, this is our first topic in our new topic set. So I know we just got done taking tests, we just got done doing a lab report, and the last topic was all about motion, or motion at least in one dimension. Okay, so now how do we transition into this new topic? Well, the new topic is now two-dimensional motion, two-dimensional kinematics. So really this one is going to be an easy one if you got what we were doing last topic, okay, or last set, because we're now taking everything that we did in one dimension and we're applying it now in two dimensions, okay? So we're now going to have two-dimensional things. Now, the biggest cause or biggest problems that I see when students move from one-dimensional kinematics to two-dimensional kinematics is that we're now looking at trig issues, okay? So now we do a lot more of this right triangle trigonometry, and it all starts right here at the very beginning with vectors. Okay, so we're now back talking about vectors again, and if you remember, a vector is a quantity that has magnitude and direction. The one thing that we always did whenever we represented a vector was we represent it with an arrow. Okay, you may remember the day that we went out into the hallway and I had you guys roll a die and flip a coin. So the coin told us which direction we were going to go, east or west, and the dice told us the magnitude, or how many steps we were going to take. Well, it's the same thing now, except that now we're not only going to move in, say, an east-west direction, but we can now also move in, say, a north-south direction. And so we now have arrows that go in kind of opposite directions. And this is why direction is so important when we start talking about vectors, okay? So again, we're looking at vectors again, and let's go ahead and get started. You'd like to see that the first picture I pulled out was a map, okay? And that's going to be one of our first activities that we're going to do in class, is we're going to make a map or draw a map of your house to the school, and we're going to look at it in the terms of vectors, okay? In terms of north, east, west, south, directional components. And if I do the same thing here, and convention says that north is always the up direction, so this is my north, I'm looking at my ship, and I want to get my ship to the treasure, or the big red X, okay? If I were to kind of draw this out, and I'm going to only draw things in kind of north, south, east, and west arrows, okay? I'm going to show this using vectors. If I look at the starting position and I go up to this point here, I create an arrow. Now this arrow happens to have a big magnitude. So I may have a direction, okay, north, and I may have to go like, 500 paces north. Okay, so again, typically we're probably talking paces or some kind of distance. Then what we had to do is we had to turn and we had to go east, and we went this direction to a certain point, and we then have another arrow that goes that direction. Now, typically when we draw our arrows, we like to draw them from the tip to the tail, and that's what I'm doing. So this is the tip of my arrow, this is the tail of my arrow. And so it shows my direction as I'm going. I then go south for a ways, okay? And then I end up having to go east for a ways. And then I end up going south again. And then I go east. And then I go north again. Then I had to maybe do a little jog back here to the west, back north again, and then east. Now that's kind of how we can draw this out if I was drawing straight lines north, east, south, and west. A lot of times we don't get a chance to do that, but this is kind of how we look at it. Now typically when we do vector addition in this sense, I'm going to refer to anything that goes this direction as one way to look at things, and anything that goes this direction as another way. Okay? So it's kind of like when we were walking the halls. So if we were one direction is positive and the other direction would be negative, and any arrow going this way would add and any arrow going this way would subtract. Well, the same is going to be true, except now we're going to have two different directions that we have to watch out for. So in other words, this big long arrow right here that goes up, that's going to be one arrow that goes this way, and then this arrow goes this direction. Okay, so they are going in opposites of each other, and so they actually cancel. And so we see then a resultant, and now this is going to be kind of our key thing, is we use a resultant when we add two vectors together. And so my resultant is that I've displaced myself north this much. Okay, I then have another arrow that comes south, I have another arrow that goes north, I have another arrow that goes north, and so all my north, north, norths would go together. So I'd have one big north here, plus this little north here, okay, plus this little north here, and so all my north arrows would add together. All of my south arrows would subtract. Okay, so I have a south arrow that subtracts here, and I have a south arrow that subtracts here. Okay, and then I look at it and I get my resultant. Okay, now essentially this arrow and this arrow are the same size, have the same magnitude, so they cancel each other out. Okay, I moved this many, like 20 paces to the north, and then I ended up moving 20 paces to the south. My net result is 0 paces. Same thing's going to be true with this arrow and this arrow. They kind of cancel each other out as well. And so my net direction then is that I went this many paces to the north. So I'd have one vector that would go that direction. The next thing I do is I look at everything in kind of my east-west direction. So anything going this direction, so I may define east as positive. So my eastward is my positive, just like I said my northward was my positive. So if I go east, I went this direction and I went this direction, so I have a little arrow going this way, I have another little arrow going this way, I'm adding the magnitudes of those arrows. I have another arrow that goes this way, I add the magnitudes of that, I have another arrow that goes this way, okay, I add the magnitude of that, and then I have this one little arrow that goes back this way, and I would end up subtracting that because, again, the arrow is going in the negative direction. So arrows going in the positive direction are going to add, arrows going in the negative direction are going to subtract. Now my net result is that I probably ended up going net this far. So my net result would be something like this. So from this point to this point was out here. Okay, so my net result was that. So in other words, this arrow and this arrow probably canceled each other out a little bit, or at least to a certain extent. Okay, so I have now my resultant in the northward direction, so resultant in the northward direction, and I have a resultant in the eastward direction. And I look at this and I say, well, so I had to go this many north and I had to go this many east, and that got me there, or I could have gone this many east and this many north, and that would have gotten me there. But why didn't the pirates just take the direct route, which would be to go from here to there? Okay, and that's what we call the resultant of these two vectors. So my resultant vector is the combination of these. My y direction vector, my x direction vector, if I start terming it that way. So again, it's about taking vectors and combining them together. Now there are situations where maybe our vectors don't have nice north, east, west, south components. That means that we may have to split vectors apart, okay? And we may have to get them onto north, east, west, and south. And so typically, like this one right here kind of meandered around. So maybe this would have been better to be in a direction like this. So I would usually have an angle that's associated with it, and I usually say my angle is like so many degrees north of south or east of west or something like that. Okay? So let's go ahead and take a look at how we deal with resultants. So now this is taking a resultant vector and we're going to switch it into its components. Okay? And so I'm going to take this magnitude of 25 meters per second. So it's a velocity. We can deal with velocities the same way as we deal with displacements. And it has an angle that it makes there. What I'm really looking for is I'm looking for a triangle. So I'm going to make a triangle right here. Okay? And remember that this arrow right here represents the component of this vector that's in this direction. It's in this direction. And this arrow represents the component of it that goes in this direction. Well, if I bring this over, I can make a rectangle out of this, and then I can see that I have two right triangles, this angle being 15 degrees, this angle being the complement of that 15 degrees. I typically like to look at this and say, okay, how do I find this side? How do I find this side? And remember that this side here is the same as this side here, and this side here is the same as this side here. That's why it's a rectangle. So I look at this and say, well, there's got to be these trig functions, okay? And so I'm going to go SOHCAHTOA, okay? SOHCAHTOA is the way that we remember which trig function to use, okay? So it's the sine is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, the tangent is the opposite over the adjacent. So now I'm going to set this up, and I'm going to say, well, what is this side? And I'm going to look at this. This is my hypotenuse. In fact, I'm going to say that this is my side opposite. This is going to be my side adjacent. Okay? And so if I took the sine of 15 degrees, it's equal to my side opposite over my hypotenuse, and my hypotenuse was 25. So I just have to then take and move the 25 over. So 25 times the sine of 15 is equal to the side that I'm looking for, or my y component. Okay, I'm going to grab my calculator. Now this is one of those things that you may need to double check and make sure that you're in degree mode, not in radian mode when you do problems in here. I know your math classes like to be in radian mode. We like to be in degree mode. So if I take 25 times the sine of 15, I get my answer, and so it says that I'm going to be going 6.47. Now this would be labeled as meters per second. So I could be going this direction, okay, this direction, 6.47 meters per second. Okay, I'm going to do the other component. The other component is now going to be the cosine of 15 is equal to my adjacent over my hypotenuse. And so I'm going to do the 25 cosine 15. 25 cosine 15. And I get the answer there. And this says that I'm going to be traveling at 24.1 meters per second. Okay? And so that's how we can split things apart. And once we get everything split apart into east, west, north, south components, x, y's, we can then add x, y's together, or add x's together, add y's together, and then we can maybe put things back into a big resultant. And this is how we go ahead and we make a bigger resultant. So now we're going to make our components become resultants. To do this, again, I look at it in terms of a triangle. So again, this side is also 44. This side is also 18. Okay, either side, it doesn't make any difference. But it's a right triangle, which means that I have this other thing called the Pythagorean theorem, a squared plus b squared equals c squared. So if I'm looking for the hypotenuse, which is my c, this is my a, this is my b, I just have to take those values and square them. So if I do 44 squared plus 18 squared, and then take the square root of that, that'll give me my c. Okay? And so I'll do that on my calculator. 44 squared plus 18 squared. Get that answer, and then take the square root of my answer. And it gets me 47.5. And now in this case, again, meters per second. So if I just travel along at 47.5 meters per second, I get to the same spot as if I drove 44 meters per second and then 18 meters per second, and it would get me there at the exact same time. I'm going to kind of pause right here. I think I'll have a second video that'll be on problems, and so you'll get a chance to look at some of the problems that we deal with this as well. Okay? So until tomorrow night, enjoy, and if you have questions, ask tomorrow.